For decades, carbohydrates, especially dietary fiber, were treated as a nutritional black box, quantified by weight, categorized by solubility, and referenced in vague generalities. Food labels typically report total carbohydrate, total sugar, and fiber, but provide no insight into the molecular composition or biological activity of these components. For instance, two foods with the same total fiber content may contain completely different types of fibers with distinct physiological effects. Yet, carbohydrates are not a few things, but hundreds. Each carbohydrate is its own molecular entity composed of distinct monosaccharides, glycosidic linkages, and branching architectures. These structures define function. Structure determines digestibility, structure determines microbial specificity, structure determines health outcomes. Using the PTFI Glycomics method, we can see that dietary fiber is not as inert as once thought. For example, beta-glucans from oats and barley aren't just soluble fibers, they also act as powerful biological agents. Their unique structures enable microbial fermentation into important metabolites that stimulate secretion of GLP-1, a master hormone of metabolic health, enhancing insulin secretion, promoting satiety, and improving glycemic control. When these powerful tools are applied, these important bioactives are both measurable and mappable. With glycomics, we can probe the carbohydrate structure of a food in a way that displays its dynamic properties shaped by cultivar, growing condition, maturity, and even microbial exposure. Ripening papaya, aging legumes, and regionally adapted grains may express entirely different carbohydrate profiles, with distinct physiological and ecological roles. Knowing the exact carbohydrates present enables the design of foods with specific health benefits, such as prebiotic formulations that selectively stimulate beneficial gut microbes,